Over billions of years, Earth's continents have not stood still. They drift, collide, and slowly lock together into giant landmasses called supercontinents, only to break apart again and start a new cycle. From ancient giants like Rodinia and Pangaea to the supercontinent that will form in the distant future, the planet seems to follow a deep rhythm on the scale of hundreds of millions of years. In this episode, we explore why supercontinents keep forming and collapsing, how plate tectonics drives this grand cycle, and what it means for oceans, climate, and life itself. If you enjoy calm journeys through Earth's deep history, please like, subscribe, and share, and tell us in the comments, what would you ask about the next supercontinent to come? Thank you for watching. Now, let's begin. Earth is a single rocky planet orbiting the Sun, with a surface organized into continents and oceans that change extremely slowly when measured against human lifetimes. Over roughly 4.5 billion years, its outer shell has never been fixed. Mountain belts are built and eroded, ocean basins open and close, and the arrangement of land and sea at the surface is repeatedly reconfigured. Modern geology describes this long-term mobility in terms of plate tectonics, a framework in which the rigid outer part of Earth is divided into large pieces that move slowly relative to one another across the globe. These motions are measured in distances of centimeters per year, but when accumulated over tens or hundreds of millions of years, they are sufficient to move continents from one side of the planet to another, and to create new global patterns of land and ocean. The present distribution of continents and oceans is therefore only one temporary state among many possible arrangements that Earth has adopted through time. When continental motions are examined not just over tens of millions of years, but over intervals approaching 1 billion years, a broader pattern becomes apparent. The continents do not simply wander independently in a random fashion. Instead, there is a tendency for most of the continental crust to become assembled into a single or nearly single connected landmass, and then later to disperse into separate continents again. A configuration in which most of the planet's continental crust is joined into one connected land area is called a supercontinent, and the long-term alternation between intervals with a supercontinent and intervals with dispersed continents is called the supercontinent cycle. In this description, a full cycle consists of continental clustering into a supercontinent, a period during which that large landmass remains broadly stable, while surrounding oceans and margins continue to evolve, and a subsequent phase in which new zones of stretching and rifting develop and eventually fragment the landmass into multiple continents. Geological and geophysical studies indicate that this complete sequence of assembly, stability, and breakup takes place on timescales of several 100 million years. Many independent reconstructions and numerical models place typical intervals between major episodes of supercontinent assembly in a broad range of a few 100 million years, often falling between about 300 and about 500 million years, with some work suggesting that the pattern may extend towards about 600 million years for a full cycle. On this basis, the idea that supercontinents form and collapse every 600 million years is best viewed as a convenient way to describe a long quasi-periodic pattern in Earth history, rather than as a precise timetable that the planet follows exactly. The cycle is not strictly regular. Instead, it shows intervals of similar order of magnitude that vary from case to case, reflecting the complex way in which the outer shell of Earth reorganizes itself over deep time. Evidence for this behavior comes from global geological and geophysical data sets, which together indicate repeated large-scale clustering and dispersal of continental crust on these long-time scales consistent with a supercontinent cycle, operating through much of Earth's later history. From the perspective of daily experience, however, the cycle remains hidden. Over a human lifetime, the positions of continents appear unchanging. Coastlines seem fixed, and the motions of plates are imperceptible without careful measurement. Even over the span of written history, there is no direct sign that continents drift across the planet. Only when data from many parts of the world are combined and interpreted over hundreds of millions of years does it become clear that the present arrangement of continents is one frame in a much longer sequence. In that sequence, the continents have repeatedly participated in episodes of assembly into large land masses and subsequent dispersal into more separated configurations. The concept of the supercontinent cycle summarizes this behavior at the largest scale and provides a way to describe how Earth's surface geography changes over very long times. In this framework, the current geography with widely separated continents and large ocean basins represents a dispersed state between past and future episodes of greater continental clustering. The detailed physical mechanisms that produce this behavior and the specific past configurations that have been proposed belong to more focused levels of description. At the planetary scale used here, the key fact is that Earth's continents take part in a long-term quasi-periodic sequence of assembly and breakup that unfolds over several 100 million years at a time. Once the idea that continents move over geological time became widely accepted, attention turned to how these motions behave over intervals that are long compared with the lifespan of any individual ocean basin. In this context, it became apparent that the continents on Earth do not simply drift in a way that is random when viewed over billions of years. Instead, they show repeated episodes in which most of the continental crust becomes assembled into one connected landmass and later disperses again. Configuration in which most of the continental crust present at a given time is gathered into a single or nearly single land area is called a supercontinent, and modern definitions often require that such a landmass contain a large majority of the existing continental crust in order to qualify. Moving under the forces described by plate tectonics, the continents have passed through multiple episodes of assembly into supercontinents, and subsequent breakup, indicating that supercontinent formation is not a one-time event, but a recurrent feature of Earth history. Geological and geophysical information suggests that this recurrence is not strictly periodic, but displays a broad quasi-periodic character in which aggregation and dispersal take place on timescales of several 100 million years. The term supercontinent cycle is used to describe the long sequence in which Earth's continents repeatedly cluster into supercontinents and then disperse into more widely separated configurations, producing alternating intervals dominated by a single large landmass and intervals dominated by several major continents and large ocean basins. In this sense, the supercontinent cycle refers to a global-scale pattern that involves the whole system of continents and oceans, and it is distinct from shorter and more localized cycles that describe the opening and closing of individual ocean basins. Conceptual and numerical models, together with syntheses of geological data, indicate that one full supercontinent cycle, from the assembly of a supercontinent through its lifespan to its final breakup, typically occupies a span on the order of a few 100 million years, with many studies pointing to characteristic values between about 300 and about 500 million years, and some work suggesting that the pattern can extend towards about 600 million years between successive assemblies. When this behavior is summarized in simple language, it is therefore common to state that supercontinents form and collapse roughly every 600 million years, but this phrasing should always be understood as an approximation that stands in for a broad range of possible cycle lengths rather than a rigid clock. Reconstructions of past continental configurations show that over approximately the last 2 billion years, the continents have been gathered into supercontinents more than once, and have also spent long intervals in dispersed states and peaks, in indicators such as the ages of collision-related mountain belts. The distribution of passive continental margins and the timing of widespread volcanic and magmatic events all cluster in ways that are consistent with repeated assembly and breakup of large landmasses. These reconstructions draw on multiple independent sources of information, including paleomagnetic measurements that record past positions of continents relative to Earth's magnetic field, age distributions of granites, and detrital zircon grains that reflect episodes of crustal growth and reworking, and correlations of large-scale geological structures between now-distant continents. Each type of evidence carries its own uncertainty and biases, and coverage is uneven in space and time, especially for the oldest parts of the rock record, but when considered together they support the conclusion that supercontinent-scale clustering and dispersal has occurred repeatedly during the later half of Earth's history. The available record suggests that the supercontinent cycle is easier to trace back through the more recent part of geological time, where oceanic magnetic anomalies and well-preserved paleomagnetic data allow relatively robust reconstructions and becomes progressively more difficult to constrain in the deep Precambrian, where many rocks have been reworked or destroyed, and direct information on past plate positions is sparse. As a result, there is no single universally agreed list of supercontinents, or of the precise times at which each one assembled and broke apart, but there is broad agreement that several such episodes took place, and that the spacing between them generally falls within the same order of magnitude. Within this long sequence, an individual supercontinent appears to endure as a coherent landmass for a limited part of the overall cycle, perhaps on the order of 1 to 200 million years, while the remainder of the time is occupied by prolonged assembly and dispersal phases during which continental blocks converge or move apart and ocean basins open or close. Studies that compare geological records with models of mantle convection and plate interactions emphasize that the timing of these events is influenced by processes in Earth's deep interior, so that the cycle is better described as quasi-periodic than as strictly repeating. In current geological reviews, the supercontinent cycle is treated as a robust organizing concept for Earth's long-term tectonic and climatic evolution, and any specific numerical value for the cycle length, including a figure of 600 million years, is explicitly regarded as an approximate characterization of a variable process rather than an exact prediction for individual future cycles. Recognition that continents have shifted position across the surface of Earth over geological time rests on several independent categories of evidence preserved in rocks, fossils and ancient climate indicators, and these same records provide the observational basis for reconstructing past supercontinents and their dispersal. Early workers note the geometric fit between opposing continental margins, most famously the correspondence between the outline of the eastern margin of South America and the western margin of Africa, but coastlines are shaped by erosion and sea level change, and do not on their own define precise past configurations. Stronger support comes from the way specific rock units and large structural belts match across present-day oceans. When the Atlantic Ocean is conceptually removed in paleogeographic reconstructions, the Appalachian Mountains of eastern North America line up with mountain belts in Greenland, the British Isles and Scandinavia forming a continuous zone of deformed rocks that is interpreted as a former collision belt generated when ancestral continents converge, and similar cross-Atlantic and cross-Indian Ocean correlations link rock sequences and orogenic belts in Africa, South America, Antarctica, India, and Australia, indicating that these fragments are once joined along shared mountain systems before later separation. fossil distributions add a further independent line of evidence. Identical or closely related fossil species are found in sedimentary rocks on continents that are now widely separated by oceans, and many of these organisms are not capable of crossing deep marine barriers. Classic examples include certain freshwater reptiles and distinctive seed ferns that occur in Permian and Triassic rocks of South America, Southern Africa, India, Antarctica, and Australia. In reconstructions that bring these continents together into a single land mass, these fossil localities form coherent continuous ranges, whereas on a modern map they are scattered across separate southern continents. Climate-sensitive sedimentary deposits and glacial features also constrain past continental positions. Rocks that record ancient glaciations such as diamictites with glacial striations occur today in regions that lie at low or mid-latitudes, which would be inconsistent with their present positions if Earth's climate system has been broadly similar over long-time scales. When continental blocks are repositioned in paleogeographic models, so that these glacial deposits lie at high paleolatitudes, and coal beds and reef limestones that suggest warm wet conditions occupy lower paleolatitudes, a more consistent pattern emerges for multiple time intervals, and these geological indicators show that continents occupy different latitude bands at different times, and support the conclusion that large horizontal motions of land masses take place over hundreds of millions of years. A major advance in quantifying continental motions arises from paleomagnetism, the study of remanent magnetization acquired by rocks as they form in Earth's magnetic field. The inclination of this magnetization provides an estimate of the latitude at which a rock forms, while its declination can be used with additional assumptions to infer the orientation of the continent. When paleomagnetic data from rocks of different ages on a single continent are assembled, they define an apparent polar wanderpath that traces how the magnetic pole would appear to move relative to that continent through time. Different continents yield different apparent polar wanderpaths. When these paths cannot be made consistent with a single moving pole, the interpretation is that the continents themselves have moved relative to each other and to the underlying mantle. By rotating and translating continental blocks until their paleomagnetic paths are compatible, geologists construct quantitative reconstructions of former continental positions and orientations for multiple time slices and gain numerical constraints on the latitudes and relative positions of continents at key stages in supercontinent assembly and breakup. Additional information comes from the age patterns of oceanic crust and seafloor magnetic anomalies, although the present oceanic plates are young in comparison with the age of the continents. Symmetric stripes of normal and reversed magnetic polarity on either side of mid-ocean ridges record seafloor spreading through time, and the increase in ocean crust age away from spreading centers demonstrates that ocean basins widen as new crust forms and older crust moves away, so that most crust in present ocean basins is younger than about 200 million years, even though the continents contain rocks that are billions of years old. Although oceanic lithosphere is continuously recycled at subduction zones, these data confirm that plates diverge and converge, and they provide boundary conditions for reconstructions of supercontinent breakup for the more recent part of Earth history. For older intervals where no ancient oceanic crust is preserved, indirect proxies such as peaks in the age distribution of detrital zircon grains, global compilations of collision-related granites, and the timing of major orogenic belts are used to identify times when large volumes of continental crust are assembled and reworked. Clustering of these signals around certain age ranges is interpreted as reflecting repeated episodes of continent-continent collision and crustal thickening that accompany supercontinent assembly followed by quieter intervals in which dispersed continents experience more passive margin sedimentation. By combining paleomagnetic reconstructions, correlations of rock units and mountain belts, fossil distributions, climate indicators, and age spectra from crustal and sedimentary rocks, geologists delineate intervals in which continental crust is concentrated into large connected landmasses and intervals in which it is dispersed, and the resulting reconstructions specify the broad timing and geometry of the recognized supercontinents in the geological record. The earliest widely recognized supercontinent in the geological record is commonly referred to as Columbia, also known as Nuna, and it represents the first time for which there is reasonably coherent global evidence that most of Earth's continental crust is gathered into a single connected landmass. Reconstructions place Columbia in the early to middle part of the Proterozoic eon, with assembly generally inferred to have been completed during a long interval of continent-continent collision more than 2 billion years ago, and its breakup beginning sometime after roughly 1.5 billion years ago, although the exact timings depend on the specific reconstruction. The argument that Columbia or Nuna exists as a supercontinent rests on the identification of global networks of collisional mountain belts of similar age on multiple now separated continents, together with paleomagnetic and geochronological data that allow those fragments to be repositioned into a coherent configuration. In many models, the cores of present-day Laurentia Baltica Amazonia parts of Africa, India, Australia, North China and Siberia are all linked along collisional belts, whose rocks record crustal thickening metamorphism and granite emplacement during a broad time window in the early Proterozoic. These belts, when traced across different cratons, define sutures where continental blocks once met, and their similar ages and tectonic styles suggest that they formed as part of a global-scale assembly event, rather than a series of unrelated local collisions. Paleomagnetic data from rocks of appropriate age on several of these cratons indicate that they occupied latitudes and orientations that can be brought into mutual agreement when the cratons are arranged in specific relative positions. When combined with the distribution of the collisional belts and age patterns of magmatic and sedimentary rocks, these paleomagnetic constraints support the view that the continental fragments once formed a single large landmass during the early Proterozoic, even though the precise outline of that landmass and the exact relative positions of individual cratons remain uncertain and differ between published models. In some reconstructions, Columbia or Nuna is envisaged as a supercontinent that is assembled by the progressive closure of multiple ocean basins between older continental fragments with the final stages of collision, producing a network of orogenic belts that encircle a large central continental nucleus. In these models, Columbia then persists as a relatively stable entity for a significant interval with subsequent tectonic activity, dominated by intraplate deformation, limited rifting, and the development of new sedimentary basins along its margins and interior. Other reconstructions place more emphasis on ongoing accretion and reorganization around the margins of the supercontinent, with substantial additions of juvenile crust and continued subduction along long-lived convergent boundaries, so that the configuration of Columbia evolves through time, even while most of the continental crust remains part of one connected landmass. There is also discussion in the literature about how sharply Columbia can be distinguished from older and younger stages of continental aggregation. Some authors treat Columbia or Nuna as the first clearly traceable supercontinent in Earth history, marking the start of a more regular supercontinent cycle, while leaving open the possibility that earlier, less well-constrained episodes of clustering may have occurred in the Archean eon, but are no longer easily reconstructible due to overprinting and loss of the oldest crust. Others emphasize that Columbia's breakup leads directly into a long interval of tectonic evolution that includes the assembly of the later supercontinent Rodinia, with some models suggesting partial overlap or transitional configurations rather than sharply separated supercontinent states. The timing and style of Columbia's breakup remain active topics of research. Indicators such as the appearance of widespread rift-related sedimentary basins, mafic dike swarms, and large igneous provinces of appropriate age on several continents are interpreted as signs that the supercontinent begins to fragment during the middle Proterozoic opening new ocean basins and initiating a transition towards more dispersed continental configurations. Recent numerical modelling studies suggest that the breakup of Nuna and the associated reorganisation of plates and mantle flow may have had significant effects on ocean basin geometry, carbon cycling, and the distribution of shallow marine environments, although the details of these links are still under investigation and are constrained by incomplete geological records for this part of Earth history. Despite these uncertainties, the existence of an early Proterozoic supercontinent that gathers a large fraction of the continental crust into one connected landmass is widely supported, and Columbia or Nuna is therefore generally regarded as the first member of the sequence of recognized supercontinents that extends through Rodinia Pannotia or Greater Gondwana, and finally Pangaea. In discussions of the supercontinent cycle, Columbia occupies the role of the earliest well-documented assembly breakup episode within roughly the last 2 billion years, providing the starting point for analyses that compare the spacing duration and tectonic characteristics of later supercontinents and evaluate how closely the cycle approximates a quasi-periodic pattern with characteristic times on the order of several hundred million years. Rodinia is the name given to a Neoproterozoic supercontinent that follows Columbia or Nuna in most reconstructions and represents a major episode in which a large proportion of Earth's continental crust is again gathered into a broadly connected landmass. Geological syntheses and paleomagnetic compilations commonly place the main assembly of Rodinia during the interval from roughly 1,100 million years ago to about 900 million years ago, with the supercontinent then existing in some form until it begins to fragment between about 800 million and 700 million years ago, although the exact limits of these time ranges differ between individual studies. In many reconstructions, the continental nucleus of present-day Laurentia occupies a central position within Rodinia, surrounded by cratonic blocks that correspond to parts of Amazonia, West Africa, Baltica, Siberia, Australia, India, South China, and other present-day regions. The inference that such a configuration exists is based on the distribution of collisional and accretionary orogenic belts of late Mesoproterozoic to early Neoproterozoic age around Laurentia and neighbouring cratons, together with paleomagnetic data and comparisons of sedimentary and magmatic histories on different continents. Grenville Age belts, which record crustal thickening metamorphism and large volumes of granite emplacement between about 1,200 million and 1,000 million years ago, lie along the present-day margins of Laurentia and have correlatives of similar age and tectonic style on other continents, and these belts are widely interpreted as sutures formed during the assembly of Rodinia. When these orogenic belts and associated crustal provinces are traced across now separated continents, they define patterns of collision that are most simply explained if many of the major cratons are joined in a single, connected landmass during the late Mesoproterozoic and early Neoproterozoic. Paleomagnetic measurements from rocks of this age provide estimates of the latitudes and orientations of individual continents at different times, and by seeking configurations in which the paleomagnetic poles from multiple cratons are mutually consistent, geologists obtain families of viable Rodinia reconstructions. However, because time-averaged geomagnetic fields are approximately axis-symmetric, paleomagnetic data alone constrain paleolatitude more strongly than paleolongitude, meaning that several different relative positions of continents along lines of latitude can satisfy the same set of paleomagnetic poles. As a result, there is no single universally accepted map of Rodinia, but rather a set of models that share certain common features, such as a central Laurentia and encircling late Mesoproterozoic origins, while differing in the exact locations and relative rotations of individual cratons. In some widely discussed reconstructions, for example Australia and East Antarctica, lie adjacent to western Laurentia, whereas in alternative models they occupy positions outboard of eastern or northern Laurentia. Similar differences apply to the proposed locations of Siberia, South China, and other blocks. The relationship between Rodinia and the earlier supercontinent Columbia or Nuna is also an active topic of analysis. Some studies treat Rodinia as a largely new configuration, assembled by substantial reorganization of continents after the breakup of Nuna, whereas others emphasize that the transition from Nuna to Rodinia may involve partial retention of earlier connections combined with accretion and collision around a pre-existing core. In this view, the late Mesoproterozoic episode associated with Grenville Age orogenesis marks a major reconfiguration in which continental blocks are rearranged into a new supercontinent state, while some deeper lithospheric elements and long-lived convergent margins persist from the preceding Nuna configuration. Following its assembly, Rodinia appears to persist as a broadly coherent landmass for a significant interval, during which tectonic activity is focused along its margins and in internal belts. Sedimentary records from this time show extensive intracratonic basins and passive margin successions on the edges of the supercontinent, while igneous records indicate continued subduction and magmatism along some external boundaries. Over time, indicators of stretching and thinning, such as rift-related sedimentary basins, mafic dike swarms, and large igneous provinces of Neoproterozoic age, become more widespread on several margins, and these are interpreted as the early stages of Rodinia's breakup. The fragmentation of Rodinia is inferred to take place in several steps, rather than through a single simple splitting event. Geological and paleomagnetic data suggest that different parts of the supercontinent begin to rift at different times, opening a series of new ocean basins and rearranging the positions of its constituent cratons. Some reconstructions describe the development of broad ocean domains, such as a Proto-Pacific or Panthalassa-type ocean, and the forerunners of later oceans like the Iapetus, around and between the dispersing continental blocks. As rifting continues, a new seafloor is created between separating fragments. Rodinia loses its identity as a single connected landmass and gives way to more dispersed continental configurations, in which some groupings of cratons begin to form the core of the next recognized supercontinent stage. The late Neoproterozoic interval following the onset of Rodinia's breakup is associated in several models with the progressive assembly of a configuration often termed Pannotia or Greater Gondwana, in which the cratons that will later constitute the Paleozoic continent of Gondwana are joined with Laurentia Baltica and Siberia in a short-lived supercontinent state. In these scenarios, the dispersal of Rodinia's fragments and the reassembly of many of them into a different arrangement illustrate the continued operation of the supercontinent cycle, with one large-scale continental aggregation being reconfigured into another over a span of a few 100 million years. At the same time, new paleomagnetic data and detailed regional studies continue to revise earlier views of which cratons participate fully in Rodinia and how they are positioned. For example, recent work on the Sveka-Norwegian origin and associated paleomagnetic poles has called into question some earlier models that placed Baltica adjacent to Laurentia within Rodinia, instead suggesting significant latitudinal separation at certain times and requiring alternative configurations. Debates of this kind reflect both the incompleteness of the Neoproterozoic rock record and the inherent limitations of the available quantitative constraints, and they lead to a range of permissible Rodinia layouts that share a common underlying pattern of late Mesoproterozoic supercontinent assembly, early Neoproterozoic stability, and subsequent multiphase breakup into dispersed continental blocks, whose later interactions produce the next supercontinent stage. The interval following the breakup of Rodinia is associated with a set of late Neoproterozoic configurations that include a hypothesized short-lived supercontinent, commonly termed Pannosia, also known as the Vendian supercontinent or Greater Gondwana, and the progressive assembly of the longer-lived southern supercontinent Gondwana. In many reconstructions, Pannosia is proposed to form during the late Neoproterozoic Pan-African orogeny, between roughly about 650 million and about 500 million years ago, when numerous cratonic blocks that had previously been arranged around Rodinia become reorganized into a new aggregate centered on what is now Africa. This configuration is inferred to include the main Gondwana cratons of present-day South America, Africa, Arabia, Madagascar, India, Antarctica, and Australia, together with Laurentia Baltica and possibly Siberia, before it begins to fragment again in the late Ediacaran and early Cambrian as new oceans, including the Iapetus Ocean, open between its components. The case for Pannosia as a distinct supercontinent rests on the recognition that a widespread system of Neoproterozoic, collisional, and accretionary orogens, collectively termed Pan-African or Brasiliano belts, records the convergence and welding of the Gondwana-affiliated cratons during this time, and that paleomagnetic and geological data permit the assembly of these blocks into a largely contiguous landmass that also maintains links to Laurentia Baltica and other continents inherited from Rodinia. In this picture, Rodinia's breakup involves the outward movement of Laurentia and other blocks from an earlier configuration, followed by a late-stage reaggregation in which Africa-centered Gondwana and additional cratons form a new supercontinent state before separating again as the Iapetus and other ocean basins develop. However, the existence of Pannosia as a fully assembled supercontinent distinct from early Gondwana is debated. Some authors argue that the geological and paleomagnetic record is better described in terms of a protracted transition from Rodinia to Gondwana, during which convergent margins and collisional belts migrate and reorganize without necessarily producing a single moment at which most of the continental crust is gathered into one landmass. In this view, the continental blocks involved in the Pan-African orogeny are still in the process of assembly or partial separation, when the first major rifting events begin implying that the hypothesized supercontinent may begin to break apart before it can be considered fully formed. Recent work that reassesses Neoproterozoic geochronological and structural data has explicitly questioned whether Pannosia satisfies commonly used criteria for a supercontinent, pointing out that the degree and duration of continental clustering in this interval may not match that inferred for Rodinia or Pangaea. Despite these differences in interpretation, there is broad agreement that the late Neoproterozoic is a time of extensive continental collision, crustal thickening and magmatism associated with the convergence of the cratons that constitute Gondwana, and that by the earliest Cambrian most or all of the Gondwana blocks have been amalgamated into a large southern supercontinent that includes present-day South America, Africa, Arabia, Madagascar, India, Australia, and Antarctica. Geological syntheses and reviews generally place the assembly of this Gondwana supercontinent as largely complete by late Precambrian to earliest Cambrian time, around about 600 to about 540 million years ago, with only smaller ocean basins still closing along some internal sutures. The assembly of Gondwana is recorded in several major collisional and accretionary belts, including the East African origin, the Kunga origin, and the Brasiliano belts of South America, which together reflect the closure of multiple ocean basins between African, South American, Indian, Antarctic, and Australian cratons. These origins preserve high-grade metamorphic rocks, widespread granitoid magmatism, and complex structural patterns that indicate repeated episodes of subduction arc accretion and continent-continent collision. Geochronological data from these belts constrain the timing of these events and show that different sectors of Gondwana assemble over an extended interval, with East Gondwana, Australia, Antarctica, India, and related blocks already forming a relatively coherent entity by about 1,000 million years ago in some models, and West Gondwana, South America and Africa, joining later during the Pan-African Brasiliano orogenic phase. Paleomagnetic poles and sedimentary records provide additional constraints on the configuration and evolution of Gondwana. Paleomagnetic data indicate that once assembled, Gondwana occupies predominantly southern paleolatitudes during the early Paleozoic and later reconstructions, show the supercontinent extending from near the South Pole into low southern latitudes. Sedimentary successions across many parts of Gondwana record a shift from late Neoproterozoic, rift-related deposits to early Paleozoic passive margin and intracratonic basin sequences consistent with a change from convergent to more stable tectonic regimes along large parts of its perimeter following assembly. These observational lines are combined with numerical models of plate motions and mantle convection to infer that Gondwana remains a major long-lived supercontinent scale aggregation throughout much of the Paleozoic, participating in the later formation of Pangaea when it collides with Laurasia during the late Paleozoic. In analyses of the supercontinent cycle, the late Neoproterozoic and early Paleozoic record is therefore described using two closely related but not identical concepts: a possible short-lived supercontinent, Pannotia, or Greater Gondwana, in which Gondwana-related blocks and other continents are temporarily assembled before rapid reorganization, and the more robustly defined Gondwana supercontinent whose existence and configuration in the early Paleozoic are strongly supported by geological and paleomagnetic data. Whether Pannotia is recognized as a separate supercontinent stage or viewed as a transitional configuration within the broader Gondwana assembly affects how the boundaries of individual supercontinent cycles are drawn, but does not alter the observation that in this part of Earth, history continental crust passes through a major episode of large-scale clustering that follows the breakup of Rodinia and precedes the later assembly of Pangaea. Pangaea is the name given to the most recent well-established supercontinent, a late Paleozoic to early Mesozoic configuration in which most of Earth's continental crust is gathered into a single connected landmass. In widely used reconstructions, Pangaea assembles from earlier continental units, notably Gondwana in the south, and a set of northern continents that include Laurentia Baltica and associated terrains often grouped as Laurasia or Laurussia during the late Carboniferous period, with assembly largely complete by around between about 335 and about 300 million years ago. In these models, Pangaea then persists through the Permian period and into the early part of the Triassic period before beginning to fragment near the boundary between the Triassic and Jurassic periods around about 200 million years ago. During its lifetime, Pangaea occupies a large fraction of Earth's surface area, with its landmass extending from high southern to high northern paleolatitudes and wrapped around much of the globe, while the remaining surface is dominated by a surrounding superocean known as Panthalassa and additional oceanic domains including forms of the Tethys Ocean. The term Laurasia is commonly used for the more northerly part of this supercontinent, comprising regions that correspond broadly to present-day North America, Europe, and much of Asia, whereas Gondwana in this context refers to the more southerly aggregation of what are now South America, Africa, Arabia, India, Antarctica, Australia, and related fragments. Together, these northern and southern components form the single supercontinent state termed Pangaea. The assembly of Pangaea is recorded in a series of late Paleozoic collisional origins that document the closure of major ocean basins between the northern and southern continental blocks. One key feature is the closure of the Rhyic Ocean, which lies between Gondwana and Laurasia during much of the early Paleozoic, and is consumed as these continents converge during the Devonian and Carboniferous periods. The final suturing of Gondwana to Laurasia along this zone produces a vast collisional orogenic system that includes the Varuscan origin of Western and Central Europe, the Alleghanian and Ouachita origins of Eastern and Southern North America, and related belts that can be traced into Mexico and other regions together, forming one of the largest collisional mountain systems of the Phanerozoic. The earlier Iapetus Ocean, which separates some of the northern continental blocks, also closes during this general interval, and its sutures are preserved in mountain belts such as the Caledonides of Scandinavia, the British Isles, and eastern Greenland. When the Atlantic Ocean is removed in paleogeographic reconstructions, these late Paleozoic and older origins link across current ocean basins into continuous belts, supporting the interpretation that the continents they occupy were once joined along major collision zones during Pangaea assembly. Additional evidence for the existence and configuration of Pangaea comes from paleomagnetism, fossil distributions, and climate-sensitive sedimentary deposits. Paleomagnetic poles derived from late Carboniferous Permian and early Triassic rocks on multiple continents can be made mutually consistent when those continents are positioned to form a single connected landmass, and the resulting reconstructions show a supercontinent that straddles the equator and extends to high latitudes in both hemispheres. Fossil assemblages of land plants and vertebrates, including distinctive groups that are unlikely to have crossed broad ocean barriers, display coherent ranges when plotted on a Pangaea base map, whereas on a modern map they are scattered across South America, Africa, India, Antarctica, Australia, Eurasia, and North America. Paleoclimate indicators show patterns in which glacial deposits, coal-bearing strata, evaporitic sediments, and reef limestones occupy latitude bands and environmental settings that are compatible with general circulation models when continents are arranged into a Pangaea configuration, including extensive late Paleozoic glaciation on southern Gondwana and more arid conditions in parts of the continental interior. Together, these lines of evidence support the conclusion that during late Paleozoic and early Mesozoic time, the continents are joined into a single large supercontinent, rather than existing as widely separated land masses. The subsequent breakup of Pangaea is a multi-stage process that transforms this single supercontinent into more dispersed continental configurations and eventually into the pattern of modern continents. Initial signs of fragmentation appear in late Permian and Triassic times, when rifting and associated magmatism develop in several regions, but the main phase of breakup is usually placed near the Triassic-Jurassic transition, around about 200 million years ago, when widespread magmatism in the Central Atlantic Magmatic Province and associated rifting mark the opening of the Central Atlantic Ocean between what are now North America, South America, Africa, and Europe. As this and related rift systems progress to seafloor spreading, Pangaea is divided into a northern landmass Laurasia and a southern landmass Gondwana separated by growing ocean basins including the early Atlantic and the Tethys domain. Subsequent phases of breakup during the Jurassic and Cretaceous periods further fragment these large units. Gondwana separates into Africa, South America, India, Antarctica, Australia, and smaller blocks as new ocean basins such as the South Atlantic and parts of the Indian Ocean open, while Laurasia is progressively divided as the North Atlantic widens and other plate boundaries evolve. By the early Cenozoic, most of the present-day continents occupy distinct plates, with substantial oceanic separations between them, and only smaller remnants of Pangaea's earlier connections persist in the form of sutures shared mountain belts and matching passive margins on opposing continental edges. Estimating the length of the supercontinent cycle requires choosing what is meant by one full cycle and deciding which geological features best mark its beginning and end, because different choices yield somewhat different numerical values even when they are based on the same underlying record. In practice, many studies define a full cycle as the interval between successive assemblies of supercontinents. Others measure from the onset of one breakup to the onset of the next, and still others compare the timing of more diffuse indicators such as peaks in collision-related mountain building, large igneous province activity, or changes in average plate velocities. Despite these differences in definition, most modern syntheses agree that the supercontinent cycle operates on timescales of several hundred million years, and many reviews cite typical cycle lengths between about 300 and about 500 million years, with some authors extending the plausible range towards about 600 million years to accommodate uncertainties in the timing of assembly and breakup. When the recognized supercontinents of roughly the last 2 billion years are considered, one approach is to identify a characteristic time for each assembly and then compare the spacing between those times. If Columbia or Nuna is treated as assembled mainly in the interval between about 2 billion, 200 million, and about 1 billion 200 million years ago, Rodinia as assembled mainly between about 1 billion 200 million and about 600 million years ago, and Pangaea as assembled during late Paleozoic time, round about 336 to about 300 million years ago, then the intervals between these episodes are of the order of several hundred million years, and depending on whether midpoints or leading edges of the assembly windows are used, can be of order 800 million years for the transition from Columbia to Rodinia, and of order 600 million years for the transition from Rodinia to Pangaea. These estimates illustrate both the long character of the cycle and the sensitivity of any single number to how assembly time is defined. A more statistical way to estimate cycle length uses global compilations of age data rather than focusing on a small set of named supercontinents. Peaks in the age distributions of collision-related granitoid rocks and of detrital zircon grains in sedimentary deposits which mark episodes of widespread crustal growth and reworking, show clustering at certain times that coincide with inferred supercontinent assembly events, and the spacing between these clustered age peaks provides an independent measure of the recurrence interval. Analyses of such age spectra have found that earlier cycles involving Precambrian supercontinents may have durations in the range of roughly 800 million years, whereas later cycles that include Rodinia and Pangaea have shorter apparent durations of roughly 400 and about 300 million years, suggesting that the characteristic timescale of the cycle may itself have evolved through Earth history, or that some episodes of assembly and breakup overlap. Other studies compare the timing of increases in orogenic frequency, long-lived plate boundaries, or large igneous provinces with models of mantle convection to infer a long-wavelength geodynamic rhythm. In these models, large-scale mantle circulation, involving the sinking of cold slabs and the rise of broad hot upwellings, produces cycles of plate convergence and divergence that influence when supercontinents are assembled and broken apart. Statistical evaluations of these records often recover a dominant timescale of around 400 to about 500 million years for major clustering in tectonic and magmatic events, broadly consistent with the supercontinent cycle inferred from paleogeographic reconstructions and age spectra, and they provide a physical context for the quasi-periodic nature of the cycle, even though they do not fix an exact value for its length. A further complication arises from the fact that different authors apply different criteria for what qualifies as a supercontinent, especially in the Precambrian record, where paleogeographic reconstructions are less well constrained. Some definitions require that a supercontinent contain a large majority, for example more than about 3/4 of the continental crust, present at that time, whereas others accept any grouping that brings most major cratons into a single connected landmass. Under the stricter criterion, some configurations such as Gondwana on its own may be excluded, while under looser criteria they may be included as supercontinents, or as parts of broader supercontinent states like Greater Gondwana. How these borderline cases are treated affects the counted number of cycles and the measured interval between them. For example, if a short-lived late Neoproterozoic configuration such as Pannotia is considered a separate supercontinent stage distinct from both Rodinia and Gondwana, the effective cycle length between assemblies would be shorter than if only Rodinia and Pangaea are counted as successive major supercontinents in this part of Earth history. In addition, there is debate over the extent to which the earliest episodes of continental clustering in the Archean and Paleoproterozoic eons should be regarded as fully developed supercontinents or as supercratons and large continents, and including or excluding these older entities changes any attempt to define an average cycle length over the entire age of the planet. Because of these definitional issues, the incompleteness of the older rock record, and the intrinsic variability in how continental plates interact, most recent reviews emphasize that the supercontinent cycle is quasi-periodic, meaning that it has a characteristic timescale of the order of several hundred million years, but does not repeat with a fixed period like a mechanical oscillator. In this context, expressing the cycle in simple language as one that causes supercontinents to form and collapse roughly every 600 million years is a convenient way to convey that the relevant timescale is very long and somewhat comparable across multiple cycles, provided it is explicitly understood that individual intervals may be shorter or longer, that uncertainties in reconstruction are large, and that the geological record supports a broad range of possible cycle lengths rather than a single exact figure. The assembly and breakup of supercontinents influence Earth's long-term climate by changing the distribution of land and sea, the geometry of ocean basins, the pathways of ocean and atmospheric circulation, and the efficiency of geochemical cycles that regulate greenhouse gases such as carbon dioxide. Studies that combine paleogeographic reconstructions with climate and ocean circulation models show that when most continental crust is aggregated into one large landmass, the continental interior tends to be relatively dry and strongly seasonal because moisture from the surrounding oceans has to travel long distances over land and is often lost as precipitation closer to the coasts. In such configurations, large parts of the continental interior are expected to experience high temperature contrasts between seasons and limited precipitation, whereas coastal regions and areas near seaways may support more humid climates. Reconstructions and modelling work for Pangaea, the best documented supercontinent, indicate that its interior is characterized by arid to semi-arid conditions and strong seasonality, while more humid belts occur along some margins and equatorial regions. Geological evidence, including widespread red bed successions, evaporites, and aeolian sandstones in continental interiors, is consistent with this pattern, and climate model experiments reproduce dry interior conditions and strong monsoonal circulation around the margins of Pangaea. The latitudinal position of a supercontinent also matters. When a supercontinent lies mainly at high latitudes, large areas of land can host continental ice sheets, especially when atmospheric carbon dioxide concentrations are low, and these ice sheets affect global climate through their high reflectivity and influence on sea level. Gondwana, for example, spends much of the late Paleozoic at high southern latitudes, and its configuration is associated with an extended interval of glaciation in the southern hemisphere, often termed the late Paleozoic Ice Age. Geological records of glacial deposits on Gondwana, together with modelling of tectonic and climatic boundary conditions, indicate that the presence and movement of this large high-latitude landmass play a central role in controlling the timing and extent of glaciation and in driving long-term changes in global climate and sea level during this period. In contrast, when a supercontinent occupies more equatorial latitudes, extensive low-latitude land areas can favour intense weathering and delivery of sediments and nutrients to surrounding seas, with consequences for the carbon cycle, and marine ecosystems and climate patterns in such cases may be dominated by strong tropical monsoon systems and large-scale atmospheric circulation cells that are organised around the equatorial landmass. The supercontinent cycle also affects climate through its control on the shape and depth of ocean basins, and on the length and configuration of continental margins. The age distribution of oceanic crust, which depends on how seafloor is created and destroyed, around supercontinents influences the average depth of the ocean basins and therefore global sea level. When a supercontinent is assembled, much oceanic crust may be relatively old and dense, leading to deeper basins and lower global sea levels, whereas during and after breakup, widespread seafloor spreading creates large areas of young, buoyant oceanic crust, which are shallower and raise global sea level. Changes in the number and length of continental margins alter the area of shallow epicontinental seas, which are important sites for carbonate deposition and organic carbon burial. As the cycle proceeds, these changes in shallow marine area, together with shifts in volcanic outgassing and weathering rates, feed back on atmospheric carbon dioxide over tens to hundreds of millions of years. Reviews that couple plate tectonic reconstructions with models of the long-term carbon cycle argue that the assembly and breakup of supercontinents contribute to transitions between relatively warm and relatively cool climate states by modulating volcanic carbon input, silicate weathering and carbon burial in marine sediments. Specific examples illustrate these couplings. Numerical experiments and geological data for Pangaea indicate that its assembly and configuration influence tropical rainfall patterns, interior aridity, and the evolution of monsoon systems, while its breakup allows more continuous ocean gateways and currents to develop, redistributing heat and contributing to global climate change as the Mesozoic oceans open. Studies of earlier supercontinents suggest that similar links operate in the Precambrian. For instance, recent work on the breakup of Nuna indicates that the creation of new ocean basins and shallow seas around dispersed continental fragments increases the area of oxygenated shelf environments and enhances carbon burial, which in turn lowers atmospheric carbon dioxide and may promote cooler, more stable climates that favour the diversification of eukaryotic life. Across multiple cycles, the broad pattern is that supercontinent assembly tends to create large, often high-latitude land masses with extensive interiors and relatively limited shallow marine area, favouring strong climate gradients, pronounced seasonality, and in appropriate configurations extensive glaciation, whereas breakup increases the length of continental margins, expands shallow seas, reorganizes ocean and atmospheric circulation, and modifies long-term carbon and nutrient cycles in ways that affect global temperature and climate variability over hundreds of millions of years. At the scale of Earth's outer shell, continents and oceans are carried on tectonic plates, which are rigid fragments of the lithosphere moving slowly over a weaker underlying layer. The lithosphere includes the crust and the uppermost part of the mantle, and is divided into a mosaic of plates that fit together without significant gaps or overlaps at the surface. Each plate may contain both continental and oceanic regions, or in some cases be dominated by one type, but all plates share the property that they behave as mechanically strong units that can translate and rotate relative to neighbouring plates over geological time. In the plate tectonic framework, this rigid shell rests on a weaker, partially molten or mechanically softer zone in the upper mantle called the asthenosphere, and relative motion between plates is possible because the lithosphere-asthenosphere boundary acts as a zone of mechanical decoupling. Measurements from space geodesy, seafloor magnetic anomalies and plate reconstructions show that plates typically move at rates of roughly a few centimetres per year, with some spreading ridges moving more slowly and others more rapidly, but in all cases at speeds that are too small to detect directly in daily experience, and that become important only when integrated over tens or hundreds of millions of years. In this system, major geological features at the surface, including ocean basins, mountain belts, deep ocean trenches and volcanic arcs, arise primarily from the interactions of plates along their boundaries, rather than from isolated vertical movements inside single plates. The plates themselves are composed of two distinct types of crustal material, continental crust and oceanic crust. Continental crust is generally thicker and less dense than oceanic crust. Global compilations indicate typical continental crust thicknesses of several tens of kilometers, commonly on the order of about 30 to about 70 kilometers, whereas oceanic crust is usually only about 5 to about 10 kilometers thick. Continental crust is dominated by relatively silica-rich rocks of broadly granitic or andesitic composition with lower average density, while oceanic crust consists mainly of denser iron and magnesium-rich basaltic and gabbroic rocks. Because continental crust is both thicker and less dense than oceanic crust, it is more buoyant relative to the underlying mantle, so continental regions stand higher and form land masses, whereas oceanic crust, which is thinner and denser, lies lower and forms ocean basins. This buoyancy contrast explains why most continental crust is above sea level, and most oceanic crust is below. The age distribution of the two crust types also differs. Large areas of continental crust are hundreds of millions to billions of years old, whereas oceanic crust is continuously created and destroyed at plate boundaries, and is generally younger than about 200 million years, because older oceanic lithosphere is eventually subducted back into the mantle. These contrasts in thickness, density, composition, and age influence how plates interact at their boundaries, and help determine where mountains, trenches, and other major surface features develop. Plate boundaries are the zones where tectonic plates meet, and relative motion between plates is accommodated, and three main types are distinguished based on the sense of relative motion: divergent, convergent, and transform boundaries. At divergent boundaries, plates move apart from each other, allowing hot mantle material to rise and partially melt. The resulting magma solidifies to form new oceanic crust, and the surface expression is a mid-ocean ridge, or in some cases a continental rift that may evolve into a new ocean basin. At convergent boundaries, plates move towards each other, and the outcome depends on whether the interacting margins are oceanic or continental. Where dense oceanic lithosphere converges with less dense continental lithosphere, the oceanic plate commonly bends and sinks beneath the continental plate in a subduction zone, generating a deep ocean trench at the surface and an associated magmatic arc further inland, where fluids released from the subducting slab promote melting in the overlying mantle wedge. Where two continental blocks converge after intervening oceanic crust has been consumed, the low-density continental lithosphere resists subduction. Instead, the crust on both sides is shortened and thickened, producing wide collisional mountain belts and high plateaus that mark the site of former plate boundaries. At convergences between two oceanic plates, one oceanic plate may subduct beneath the other, forming an island, arc, and trench system. Transform boundaries are places where plates slide laterally past one another with relative motion accommodated by near-vertical strike-slip fault systems. These boundaries neither create nor destroy significant amounts of crust, but are sites of frequent earthquakes. In the global plate system, new oceanic crust is generated at divergent boundaries. Old oceanic crust is recycled into the mantle at many convergent boundaries, and lateral offsets between different parts of the plate, mosaic, are taken up along transform boundaries. Since continents are embedded in this moving lithospheric shell, their positions and mutual distances change as the underlying plates move, collide, rift, and slide past one another over time. Over hundreds of millions of years, these surface-level processes bring continents together into large connected configurations along networks of convergent and collisional boundaries, and later separate them again along rifts and spreading centers, providing the plate-scale framework in which supercontinents assemble and fragment during successive stages of the supercontinent cycle. Continental collisions and the mountain belts they produce are central surface expressions of how supercontinents assemble, because they record the final stages of ocean basin closure and the welding of once separated continents into a single connected landmass. At a global scale, the process typically begins with long-lived subduction of oceanic lithosphere at convergent plate boundaries. As oceanic plates cool and become denser with age, they tend to sink into the mantle along subduction zones, pulling attached plate segments and gradually reducing the width of intervening ocean basins. This mechanism, together with the overall geometry of plate boundaries, is responsible for the progressive convergence of continents across oceans over tens to hundreds of millions of years. While an ocean basin still exists between continents, subduction commonly creates accretionary origins along the margins of continents, where oceanic crust island arcs, microcontinents, and sedimentary prisms are added to the edges of existing continental blocks. These accretionary origins are characterized by long belts of deformed and metamorphosed rocks, magmatic arcs, and sedimentary wedges, and they may persist for hundreds of millions of years as sites of crustal growth and crustal reworking, while the continents on either side slowly approach one another. As convergence proceeds and the intervening ocean shrinks continental margins, eventually enter the subduction system. Because continental crust is thicker and less dense than oceanic crust, it resists continued subduction once it reaches the trench. Instead, the buoyant continental lithosphere tends to jam the subduction zone, and the convergence between plates is taken up by large-scale deformation, shortening and thickening of the crust in a collisional origin. In such zones, rocks from both sides of the former ocean are imbricated, folded and thrust over one another, leading to elevated plateaus and mountain ranges. Geological records from collisional origins show deep crustal metamorphism, including high and ultra-high pressure assemblages that indicate burial of continental material to tens of kilometers depth, and in some cases to pressures requiring subduction to mantle depths followed by exhumation. The deformed and metamorphosed rocks of a collisional origin often contain fragments of the vanished ocean basin, such as slices of oceanic crust and upper mantle, known as ophiolites. These elements, together with characteristic high-pressure metamorphic assemblages, define a suture zone that marks the former position of the closed ocean. Global compilations of orogenic belts distinguish between accretionary origins, which reflect continuous or episodic addition of material at active margins during oceanic subduction, and collisional origins, which form when continental blocks meet and the last remaining oceanic lithosphere is consumed. In the context of supercontinent assembly, many separate accretionary and collisional origins around different margins of spreading continents may evolve in parallel. Over long intervals, convergence around much of the periphery of a set of continents can create a subduction girdle encircling an evolving cluster of land masses. As individual ocean basins close by, subduction arcs and microcontinents are accreted, and major collisional belts form where large continents meet. The cumulative effect is to reduce the total length of oceanic plate boundaries between the major continental blocks and to increase the number and continuity of sutures linking them. Geological reconstructions of supercontinent assembly infer past configurations by tracing these collisional and accretionary belts across now separated continents, and by matching the timing and style of deformation on each side of present-day oceans. In the assembly of Pangaea, for example, multiple ocean basins are closed by subduction before final continent-continent collision, and numerical and conceptual models of that process emphasize that the final supercontinent state emerges from a long sequence of convergent interactions rather than from a single collision. Similar reasoning is applied to older episodes such as the assembly of Rodinia and Gondwana, where networks of Grenville Age and Pan-African Age collisional belts are interpreted as the surface record of a large-scale continental convergence preceding supercontinent states. In this way, the distribution age and internal structure of mountain belts, together with the sutures and former subduction zones they contain, provide the primary surface-level evidence that continents have converged along specific paths and been joined into larger entities over time, and they form one of the main observational bases for reconstructing how successive supercontinents have been assembled from smaller continental fragments. The breakup of a supercontinent at the surface begins with continental rifting, a process in which the lithosphere within a continent is stretched and thinned until it eventually ruptures and gives way to seafloor spreading and the formation of a new ocean basin. In mechanical terms, rifting involves extension of the entire lithospheric column, including both the crust and the uppermost mantle, accompanied by normal faulting subsidence and often magmatic intrusion. If stretching continues far enough, the continental lithosphere is thinned to the point where mantle material can rise to shallow depths, melt, and create new oceanic crust, marking the transition from a rift to a young ocean. Within plate tectonics, rifting is commonly distinguished as active or passive depending on the relative importance of forces applied from below and from the sides. In active rifting, anomalously hot mantle, upwellings often described as plumes impinge on the base of the lithosphere, thermally weaken it, and generate uplift and magmatism that promote extension. In passive rifting, far-field plate boundary forces such as those transmitted from distant subduction zones or ridge push place the lithosphere in horizontal tension, and thinning proceeds without requiring unusually hot mantle, although some upwelling and melting still occur as the lithosphere thins. In reality, many natural rifts probably involve a combination of these mechanisms, with both plate scale stresses and rising hot mantle contributing to the final breakup. Rifts tend to develop preferentially along pre-existing zones of weakness in the continental lithosphere, including old sutures, former orogenic belts, and long-lived shear zones that formed during earlier episodes of collision and accretion. These inherited structures have already experienced strong deformation and metamorphism, and they often contain mechanically weak rocks and fabrics that localize strain when the continent is placed under extension. Reconstructions of past supercontinents and numerical models of their breakup indicate that many major rift systems follow or intersect former collision zones, suggesting that supercontinents frequently fragment along old scars left behind by earlier assembly events. Recent geodynamic work that combines reconstructions and mantle convection modeling supports the view that while mantle plumes may provide a trigger for breakup, the location of rifts is strongly controlled by this tectonic inheritance, and that repeated Wilson cycles of ocean opening and closure occur along broadly similar structural trends. The evolution of a rift can be described in several stages. In the earliest or embryonic stage, extension produces a broad zone of normal faulting and moderate crustal thinning, with subsidence forming alongst basins that accumulate continental sediments and in some cases lakes or restricted marine deposits. As stretching continues, the crust is further thinned and the underlying lithospheric mantle is brought to shallower depths. This reduction in pressure can lead to partial melting of the mantle, and magma may intrude the crust as dikes and sills or erupt at the surface. In some rift systems, magmatic activity remains limited, and the resulting margins are termed magma poor or non-volcanic. In others, large volumes of mafic magma are emplaced, creating thick igneous sequences and extensive volcanic successions that define volcanic passive margins. When thinning reaches a critical level, the continental lithosphere ruptures, and a continuous zone of partial melting and magma supply develops beneath the former rift axis, giving rise to a mid-ocean ridge. From that point, new oceanic crust is generated by seafloor spreading, and the former continental rift shoulders evolve into opposing passive continental margins that subside thermally as the newly formed oceanic lithosphere cools and thickens. The breakup of Pangaea provides a well-studied example of how these processes proceed at supercontinent scale. Geological and geophysical data show that rifting within Pangaea begins in several regions during the late Paleozoic and early Mesozoic, including zones that eventually develop into the Central Atlantic, the North Atlantic, and parts of the Southern Atlantic and Indian Oceans. In many segments, early rifting is accompanied by widespread magmatism such as the Central Atlantic Magmatic Province, near the Triassic-Jurassic boundary, where thick basaltic sequences and intrusive complexes are emplaced along the developing rift system. Structural and stratigraphic studies show that initial extension creates half-graben basins, bounded by normal faults filled with continental sediments and volcanic rocks, and that continued extension leads to progressive thinning and eventual rupture, after which seafloor spreading begins and well-defined passive margins form on either side of the new ocean. Comparisons of timing and style between different sectors indicate that breakup is diachronous, with some margins entering a drifting stage while others remain in the rift phase, and climate and sedimentation patterns adjust as new oceanic gateways open and marine connections evolve. From a plate tectonic perspective, the birth of a new ocean during supercontinent breakup represents the opening phase of a Wilson cycle in which an ocean basin develops from initial continental rifting through a young spreading stage to a mature configuration with wide oceanic domains before eventually being closed again by subduction and continental collision. The supercontinent cycle includes many such Wilson cycles, operating in different places and at different times, some leading to large oceans that separate major continents and others creating smaller basins that close relatively quickly. Observations from present and ancient rifts together with numerical models of lithosphere stretching and magma supply show that the detailed geometry and structure of rifted margins, including their width, degree of crustal thinning, and magmatic content depend on factors such as the rate and duration of extension, the thermal state and composition of the lithosphere, and the presence or absence of strong plume-related upwellings. Current classifications of rifted continental margins therefore distinguish between end-member volcanic and non-volcanic types, and recognize a spectrum of intermediate cases reflecting the range of physical conditions under which continental lithosphere can be thinned and broken during the transition from a supercontinent to a new arrangement of continents and oceans. Beneath the moving plates at Earth's surface, the mantle behaves on long timescales as a very slow convecting solid, and the large-scale patterns of this convection provide the deeper physical context for the supercontinent cycle. The mantle extends from the base of the crust to the core mantle boundary and is composed mainly of solid silicate rocks that can deform and flow over millions of years under the influence of gravity and internal heat. Seismic tomography, which uses the way seismic waves travel through Earth's interior to infer variations in material properties, shows that cold, dense slabs of lithosphere subducted at trenches can be traced from the surface down through the upper mantle and across the mantle transition zone, in many cases continuing into the lower mantle, to depths approaching the core mantle boundary. In contrast, large, low shear velocity provinces near the base of the mantle, beneath regions such as Africa and the Central Pacific, are interpreted as broad, relatively hot, or compositionally distinct upwellings. Together, these observations support the existence of whole mantle convection, in which sinking slabs and rising hot regions participate in a linked circulation system that spans the full mantle thickness rather than being confined to separate upper and lower layers. Over geological time, this convection pattern transports heat from the deep interior towards the surface and drives stresses that help move the overlying plates. The energy that powers mantle convection comes from several sources, including heat, left over from Earth's formation, heat released by the crystallization of the core, and heat produced by the decay of radioactive isotopes in the mantle. As this heat is carried upwards by convection and lost through the surface, the overall vigor of mantle flow and the style of convection can change, but present-day mantle convection retains large-scale structures that have persisted for hundreds of millions of years. Numerical models that incorporate realistic mantle viscosity structures, internal heating and plate-like surface behavior commonly produce long wavelength convection patterns dominated by a small number of broad upwellings and downwelling regions, and the distribution of subduction zones and super plume-like upwellings in these models resembles the observed arrangement of present-day slabs and low-velocity provinces. In many such models, the presence of a supercontinent influences the pattern of mantle flow. When most continents are assembled, subduction zones tend to form a broad girdle around the margins of the supercontinent, and the accumulation of cold, dense slab material sinking along this girdle promotes the development of large-scale downwelling beneath the surrounding belt. Mass and heat conservation then favour the rise of relatively hot mantle beneath the interior of the supercontinent, either as one broad upwelling or as several large plume-like structures. This arrangement of a circum-supercontinent belt of downwelling and interior upwelling is a natural outcome in many simulations, and it provides a mechanism by which the assembly of a supercontinent can reorganize mantle flow and modify the forces acting on the overlying plates. In this setting, the concentration of upwelling mantle beneath continental interiors can raise lithospheric temperatures, contribute to uplift and enhance magmatism, while horizontal tractions and buoyancy variations generated by these flow patterns modify the stress field in the overlying lithosphere. When combined with inherited zones of weakness in the continental crust and upper mantle, these effects favour the initiation of rifting within the supercontinent at locations where pre-existing structures and mantle flow align. Over long timescales, this feedback between plate configuration and mantle convection helps explain why supercontinents do not remain stable indefinitely, but eventually fragment, initiating a new supercontinent cycle phase. Geodynamic studies that couple plate motions with mantle convection seek to quantify how large-scale flow in the mantle controls when supercontinents assemble and when they begin to break apart. In these models, the mantle is treated as a viscous convecting solid that transports heat from the deep interior to the surface, while the plates at the top boundary move collide and rift in response to stresses produced by this flow and to their own buoyancy forces. Seismic tomography shows that coal-dense slabs that sink at subduction zones can be traced from the surface into the lower mantle, and that two broad regions at the base of the mantle beneath Africa and the Pacific exhibit unusually low shear wave velocities. These large low shear velocity provinces, often termed thermochemical piles or superplumes, appear to be continent-scale structures that occupy a substantial fraction of the lowermost mantle and extend hundreds to about 1,000 kilometers above the core mantle boundary. Their present-day locations correlate with large-scale upwelling regions and with positive dynamic topography at the surface and mantle flow models that incorporate realistic density contrasts and plate histories reproduce similar basal structures. Together, these observations support the view that the deep mantle has a persistent degree 2 pattern dominated by two antipodal upwelling regions and surrounding downwelling belts, and that this structure interacts with the supercontinent cycle over hundreds of millions of years. Spherical convection calculations in which continents are treated as mechanically strong, thermally insulating caps demonstrate that assembling a supercontinent exerts a first-order control on mantle flow. When most continental area is aggregated, subduction zones are forced to lie mainly around the margins of the continental cluster, forming a circum-supercontinent subduction girdle that focuses slab descent into a ring of downwelling. In response, mass conservation and buoyancy forces organize return flow in the mantle into one or two broad upwellings away from this ring, commonly beneath the interior of the supercontinent and at a roughly antipodal location. Numerical experiments show that the onset of a supercontinent state promotes a transition from more irregular convection patterns to degree 1 or degree 2 modes dominated by one or two super upwelling regions, and a continuous band of downwelling associated with the subduction girdle. As slabs continue to sink along this band, they feed the basal thermochemical structures and help maintain their lateral extent while hot and buoyant material rises beneath the continental aggregation. In simulations that assimilate plate reconstructions for the last several 100 million years, the predicted distribution of accumulated slabs at depth and the configuration of basal upwellings broadly match the seismologically imaged African and Pacific low shear velocity provinces, and the inferred history of slab input suggests that these provinces may have been modified but not completely destroyed through successive supercontinent cycles. The presence of a supercontinent modifies the thermal and mechanical state of the overlying lithosphere. Because continental lithosphere is relatively thick and has lower effective thermal conductivity than oceanic lithosphere, it acts as an insulating lid that reduces heat loss from the mantle beneath it. Over tens to hundreds of millions of years, this insulation leads to elevated mantle temperatures under the supercontinent, relative to adjacent oceanic regions. Models that include this effect find that the growth of a thermal anomaly beneath the supercontinent increases the buoyancy of the underlying mantle, enhances vertical normal stresses at the base of the lithosphere, and can generate extensional stresses in the interior of the supercontinent of the order of several tens of megapascals. Simulations that track the stress field through the supercontinent cycle indicate that compressive stresses tend to dominate during assembly when convergent plate boundaries surround the growing landmass, but as slab piles accumulate at depth and basal heating strengthens the mean state, in the interior evolves towards extension. Under many model conditions, this change in stress regime is sufficient to initiate distributed rifting, once inherited weaknesses in the lithosphere such as old sutures and shear zones are included, and the location of maximum extensional stress often aligns with regions where these weak zones are present. Several recent analyses compare the relative contributions of forces acting on supercontinents during breakup, focusing on subduction retreat at the margins and plume-related upwellings beneath the interior. Calculations that include both processes show that the horizontal stresses generated by plume buoyancy and associated dynamic topography under a supercontinent interior can be comparable to or larger than those driven by slab pull and trench retreat at its edges, especially once a large hot upwelling has developed beneath the continental cap. In such models, plume push in the interior is identified as a dominant driver of incipient breakup, while subduction retreat and plate boundary forces help organize newly formed rifts into coherent spreading systems as the continental fragments separate. The interaction between these forces depends on how quickly slab graveyards build up at the base of the mantle, how strongly basal thermochemical piles respond to changing subduction patterns, and how efficiently heat is transferred from the core and deeper mantle into the regions beneath continents. Over multiple cycles, some models suggest that repeated focusing of subduction around supercontinents and the associated accumulation of slabs near the core mantle boundary help regenerate basal thermochemical structures in broadly similar positions so that interior upwellings remain preferentially associated with a small number of long-lived basal anomalies. The evolution of deep mantle structure over multiple supercontinent cycles is investigated using reconstructions that extend basal flow models back through earlier supercontinents such as Nunarydinia and Pangaea. One approach uses paleogeographic models to infer where long-lived subduction zones were located through time, and then advect synthetic slabs through a convecting mantle to predict where subducted lithosphere should accumulate at depth. When these synthetic slab graveyards are compared with present-day low-shear velocity provinces, there is broad overlap in location, implying that basal thermochemical structures may be repeatedly modified, but broadly regenerated in the same regions as supercontinents assemble and break up. Other work explores how mobile these basal piles are. Some models favor relatively stable positions beneath Africa and the Pacific over at least the last several 100 million years, whereas others allow significant lateral motion in response to changes in the global pattern of subduction. Studies that explicitly examine the superpeel cycle propose that low shear velocity provinces can drift and change shape as slabs are added asymmetrically, but remain broadly associated with regions of long-term slab input and plume generation. The degree of mobility inferred has implications for whether future supercontinents are more likely to form above existing basal structures or in new locations relative to them, and it remains an active topic of research. Despite these advances, important uncertainties remain in the link between mantle convection patterns and specific timings of supercontinent assembly and breakup. Mantle rheology, including the dependence of viscosity on temperature pressure, grain size and composition, is only partly constrained by experiments and observations, and different parameter choices can alter how strongly continents influence flow and how rapidly basal structures respond to evolving plate boundaries. Tomographic images have finite resolution and may smooth or underestimate the amplitude of true velocity. Anomalies and differences between independent tomography models introduce uncertainty into the exact shape and volume of low shear velocity provinces. Long-term simulations necessarily simplify plate behavior, often treating continents as rigid blocks and parameterizing subduction zones, rather than resolving the full complexity of plate boundary deformation and microplate interactions. For these reasons, geodynamic models are well suited to demonstrating that the supercontinent cycle is compatible with and likely coupled to persistent long-wavelength mantle convection patterns with degree 2 structure and repeated interior upwelling beneath continental aggregates. But they do not yet provide a unique prediction for the exact geometry or timing of any individual future cycle. At the innermost level, the supercontinent cycle depends on how rocks deform and how heat is transported inside Earth, and both of these depend on physical properties that are only partly constrained by experiments and observations. Mantle and lower crustal rocks are solid on human timescales, but flow as highly viscous materials over millions of years, and their effective viscosity varies by many orders of magnitude as a function of temperature pressure, composition, grain size, stress, and the presence of small amounts of water or melt. Laboratory deformation experiments on minerals such as olivine and feldspar geodetic measurements of present-day strain in plate boundary zones, and studies of exhumed deep shear zones together show that several creep mechanisms operate in different depth and stress regimes, and that the transition between them depends sensitively on grain size and fluid content. These results imply that the strength of the lithosphere and the convecting mantle cannot be represented by a single viscosity value, but instead requires constitutive laws in which viscosity changes strongly with temperature and other state variables, and natural shear zones indicate that deformation tends to become localized into narrow bands, where grain size is reduced and strength is lower than in surrounding rock. In numerical models of mantle convection and plate motion, these complex behaviors are usually simplified into parameterized rheologies with a limited number of adjustable constants, and plausible but not uniquely determined choices must be made for how viscosity depends on temperature, water content, grain size, and pressure and different parameter sets can produce different rates of convective overturn, different depths of slab penetration, and different patterns of upwelling, which in turn alter the predicted timing and style of supercontinent assembly and breakup. So uncertainties in rock rheology propagate directly into uncertainties in estimates of supercontinent cycle length and regularity. Experimental and theoretical work on deep mantle rheology continues to revise these parameters, and recent studies emphasize that grain size evolution, water distribution, and phase transitions all contribute to the effective viscosity structure used in geodynamic models. Heat transport in the mantle is similarly complex. Heat is supplied from radioactive decay within the mantle from secular cooling of the planet, and from heat flow out of the core, and is removed by convective transport and by conduction through the lithosphere to the surface. The balance between internal heating and basal heating from the core, and the efficiency with which convection mixes warm and cool regions, influence how vigorously the mantle circulates and how quickly it loses heat. Several recent modelling and theoretical studies suggest that feedbacks involving water cycling and partial melting can buffer mantle temperature and viscosity, producing a self-regulated evolution in which the average viscosity remains within a limited range even as heat production declines, but the detailed behaviour depends on how water is stored and transported in different mantle reservoirs and on the efficiency of melt extraction. Because present constraints on the distribution of water and melt with depth are incomplete, these buffering mechanisms are not yet tightly quantified, and different assumptions about them lead to different predictions for how the vigour and pattern of mantle convection change over billions of years. This in turn affects whether supercontinent cycles are expected to become longer, shorter, or more irregular as Earth cools and as internal heating decreases with time. At the same time, there are open questions about when plate tectonics begins and whether its style has changed, particularly during the interval in the Proterozoic that is sometimes described as a boring billion because of its relatively subdued tectonic and environmental variability. If plate interactions and mantle rheology in the distant past differ significantly from those operating during the last one or two supercontinent cycles, then simple extrapolations of present-day behaviour backwards in time may misrepresent the spacing and character of earlier cycles. The rock record from these early intervals is fragmentary, especially for oceanic crust and subduction zones, and this limits how well rheological parameters and plate configurations can be inferred, adding another source of uncertainty to any attempt to define a single characteristic cycle length over the whole age of the planet. Even in the better documented Phanerozoic, the timing and configuration of supercontinents are still subject to revision because improved paleomagnetic data and new geochronological and structural observations can change interpretations of when individual sutures form and when dispersal stages begin. A second class of uncertainty arises from the definition of what qualifies as a supercontinent and how strictly that definition is applied. Some authors require that a supercontinent include a large majority of the continental crust present at a given time, whereas others accept configurations in which most major cratons are connected, even if some small blocks or peripheral continents remain outside the main aggregation. The first definition tends to count fewer, more clearly separated supercontinent states, while the second allows additional intermediate or partial supercontinents to be recognized. Which choice is adopted alters the number of cycles identified and the intervals between them. The status of Gondwana on its own of short-lived Neo-Proterozoic configurations, such as Pannotia or Greater Gondwana, and of possible early Archean supercretons are all discussed in this context, and there is no single agreed classification that all workers follow. Because of these definitional differences, some studies treat the cycle as a sequence of a few major supercontinent stages separated by long dispersed intervals, while others view it as a more continuous process in which continental clustering and dispersion vary in degree through time. These conceptual choices again affect how the phrase every 600 million years should be interpreted when it is used to describe the supercontinent cycle. Looking forward, the same sources of uncertainty apply, and they are compounded by the fact that only one incomplete cycle involving Pangaea has been observed at high temporal resolution. Several scenarios have been proposed for how and where a future supercontinent might form, including configurations in which the present Atlantic Ocean closes and continents reassemble in a Pangaea-like arrangement, sometimes termed Pangaea Proxima or Novopangaea configurations, in which the Pacific Ocean closes and a high-latitude supercontinent, sometimes called a major, forms near the Arctic, and configurations in which both Atlantic and Pacific Ocean basins are reduced and a more equatorial supercontinent such as Orica emerges. These scenarios are generated by combining present plate motions with assumptions about how new subduction zones will initiate and how existing subduction zones will migrate, and by embedding those surface histories in models of mantle convection. They typically place the assembly of a next supercontinent on timescales of roughly 200 to about 300 million years from the present, but the divergence between different models illustrates that the outcome is sensitive to poorly constrained aspects of plate boundary evolution, such as whether subduction will propagate into the Atlantic or remain confined to the Pacific, and how long current slabs will continue to sink in their present locations. Climate simulations based on some of these future supercontinent scenarios indicate that the resulting land sea distributions would significantly alter global climate, but these results again depend on which tectonic pathway is realized and on how atmospheric composition evolves over the same interval. On this basis, it is possible to state that if present plate tectonics continues to operate, Earth is likely to experience at least one more episode of supercontinent assembly on a timescale of a few 100 million years, consistent with a quasi-periodic supercontinent cycle. But it's not possible to predict uniquely which configuration or exact timing will occur. Resolving these questions requires better constraints on mantle rheology across a wide range of depths and temperatures, improved understanding of how water and melts are cycled between surface and interior, and how they influence viscosity, more detailed reconstructions of past plate motions and subduction histories, and clearer criteria for classifying supercontinent states in the geological record, and until such constraints are available, estimates of supercontinent cycle length and future configurations will remain expressed as broad ranges rather than exact numbers,